Chapter 11, Section 2, Key Properties of Eigenvalues and Eigenvectors, Part 1. Eigenvalues and eigenvectors have some key properties that make them useful in various applications. I will explain these properties one by one. In this section, we focus on these two properties. Let's start with the first property, linearity of eigenvectors. This property says eigenvectors corresponding to different eigenvalues are always linearly independent. This means no eigenvector can be written as a combination of others when their eigenvalues are distinct. This property enables us to diagonalize the matrix because diagonalization requires a complete set of linearly independent eigenvectors. Let's take an example. For this matrix A, the eigenvalues are lambda 1 equals 7 and lambda 2 equals 1. And their eigenvectors are these v1 and v2. These two eigenvectors are linearly independent, so the matrix A can be diagonalized. Let me show you the mathematical proof of this property. Let A be an n by n matrix, and let lambda 1, lambda 2, lambda k be distinct eigenvalues of A with corresponding eigenvectors v1, v2, vk. According to the property, the set of eigenvectors is linearly independent. First, suppose that the eigenvectors are linearly dependent. That is, there exist scalars C1, C2, Ck, not all 0. Next, multiply matrix A to both sides. Since each Vi is an eigenvector of A corresponding to lambda I, applying A to the equation gives the following equation. Using the definition of eigenvectors, we can rewrite the equation in this way. Next, construct a system of equations. We now have two vector equations, so we can construct this system of equations. Consider these two equations as a system of homogeneous linear equations in C1, C2, Ck. We can write them in matrix form. If eigenvectors are linearly dependent, then the coefficient matrix of eigenvectors would have non-trivial solutions for C1, C2, Ck. It implies a contradiction because the eigenvalues lambda I are distinct. Since the eigenvalues are distinct, the system can only have the trivial solution. This means that the eigenvectors are linearly independent. Let's go on to the next property, sum of eigenvalues. This property says that for a square matrix A of size n by n, the sum of the eigenvalues of A is equal to the trace of A. The trace of a matrix A is the sum of its diagonal elements. The sum of all eigenvalues of A, including their multiplicities, equals the trace of A. Let's take an example. For this matrix A, the eigenvalues are lambda 1 equals 7 and lambda 2 equals 1. The trace of A is 5 plus 3 equals 8. The sum of eigenvalues lambda 1 plus lambda 2 equals 3 plus 2 equals 5, which matches the trace. Proving this property is a complex task. For proving, we need to understand the factor theorem. the fundamental theorem of algebra, characteristic polynomial. First, let's understand the factor theorem. For any polynomial of degree of n, this equation holds. If pa equals 0, x minus a is a factor, so px can be expressed by this equation. Here, qx is another polynomial of degree of n minus 1. If a polynomial px has a root a, that is, pa equals 0, x minus a is a factor of px. This means that if you plug in x equals a and get 0, the polynomial must be divided by x minus a without any remainder. Let's understand the factor theorem using this polynomial. If we check P2, we can say it is 0. P2. Similarly, here P3 equals 0, so x minus 3 is also a factor. This means the polynomial can be factored in this way. The next is the fundamental theorem of algebra. This theorem states that any polynomial of degree n with complex coefficients has exactly n roots in the set of complex numbers. In other words, given any polynomial of degree n, this equation holds. There exist exactly n solutions in the set of complex numbers, considering multiplicities. Let's illustrate this theorem using a quadratic polynomial. To find the roots of px, we solve this equation. This equation can be factored in this way, setting each factor to 0, and we can find the roots. So, the roots of px are x equals 2 and x equals 3. Since this is a degree 2 polynomial, the fundamental theorem of algebra guarantees that it has exactly 2 roots. If the polynomial had no real solutions, the fundamental theorem ensures that solutions still exist in the complex number system. For example, this polynomial has the roots of x equals plus minus I. Even though these are not real numbers, they exist in the complex number system Xi, satisfying the fundamental theorem of algebra. Let's go on to a characteristic polynomial. For an n by n square matrix, the characteristic polynomial is defined in this way. Here, I is the n by n identity matrix, and lambda is a scalar treated as a known variable. By solving this polynomial equation, we can find the eigenvalues of A. Let's see an example of calculating the characteristic polynomial. For this 2 by 2 matrix A, the characteristic polynomial can be defined in this way. Next, compute A minus lambda I. The determinant of this matrix can be calculated in this way. Thus, the characteristic polynomial can be defined as this equation. Now, we are ready for proving the property, sum of eigenvalues. This property says that for a square matrix A of size n by n, the sum of the eigenvalues of A is equal to the trace of A. First, define the characteristic polynomial. The eigenvalues of an n by n matrix A are the roots of its characteristic polynomial, which is defined as this equation. Expanding the determinant using the general form of a characteristic polynomial, we obtain this equation. From this expansion, we see that the coefficient of lambda to the power of n minus 1 is minus trace of A, where trace of A is the sum of the diagonal elements of A. Let's go on to the next step. By the fundamental theorem of algebra, the characteristic polynomial can also be expressed in terms of its roots. Expanding this product, we obtain this expression. Comparing this with the earlier expansion, we see that the coefficient of lambda to the power of n minus 1 in both expressions must be the same. Thus, we conclude the property holds. This result shows that the sum of the eigenvalues of A is equal to the trace of A, which is the sum of its diagonal elements. This holds for any n by n square matrix, whether it is diagonalizable or not. As an appendix, let me explain why does the general form of the characteristic polynomial hold. Before going to the explanation, let's recap cofactor expansion, also known as Laplace expansion. It is a systematic method to calculate the determinant of a square matrix by expanding along a chosen row or column. It reduces the calculation of the determinant of an n by n matrix into smaller determinants of n minus 1 by n minus 1 matrices. As the general formula, cofactor expansion can be expressed in this way. For an n by n matrix A, the determinant can be calculated by expanding along any row I or column J. Now let's explore why the general form of the characteristic polynomial holds. First, let's define a characteristic polynomial. For an n by n matrix A, the characteristic polynomial is defined as this equation. This determinant can be obtained by expanding the determinant of A minus lambda I. Now, let's go on to the derivation of induction. First, suppose a based case where n equals 1. If the matrix A is of order 1, it is a scalar, and its determinant can be expressed in this way. This form matches the characteristic polynomial's general structure. Next, assume that n equals k. For n equals k, the characteristic polynomial can be expressed in this way. Next, let me provide a case for n equals k plus 1. For k plus 1 by k plus 1 matrix A, applying cofactor expansion along the first row, we obtain this equation. Here, Mij is the determinant of a minor matrix of order k plus 1 minus 1 equals k. By the inductive hypothesis, we know that Mij can be expressed by this equation. Thus, the general form of the characteristic polynomial holds for n equals k plus 1. So we can say that the general form holds for any value of n. Thank you for watching. Please thumbs up and subscribe to my channel.